As we discussed in the previous class, introduction to control systems and various examples that come across open loop control system as well as closed loop control system. So when it comes to the comparison between them, the open loop control system will have a controller and then plant or process to be controlled, and there is an output for certain input. And in the case of closed loop control system, in addition to this, there is an error detector, then controller, then plant to get output, and there is a feedback. When you compare these two figures, you can find additionally there is a error detector and feedback network. So by seeing the circuit itself, I can say that open loop control systems are very simple. Construction of the open loop control system is very simple, whereas in the case of closed loop system, it is very complex and economical. Because no sensing mechanism, no feedback, no error detector, so it is economical, and this is costly. When it comes to the stability of a open loop control system, as less number of components involved, the stability is not a problem. So generally stable open loop control systems, whereas in the case of closed loop control system, it is very difficult to achieve stability. Now when it comes to the gain of an open loop control system, these two blocks together, when you combine, say its gain is G, even here also G, then the gain of this particular path or system is given by C of S by R of S, it is G. In the case of closed loop control system, it is given by G by 1 plus GH. So we have a factor 1 by 1 plus GH additionally. So the gain is more in the case of open loop control system. In the case of closed loop, the gain is reduced by a factor of 1 by 1 plus GH. So we need to concentrate on controller so that it should produce the desired gain and also accurate output. As I mentioned, closed loop control systems are more accurate. So when you would like to have an accurate output, there is no option, we must have to go for closed loop control system. So I can say that accuracy is the plus point of a closed loop control system, though it is complex to construct, costly and difficult, but you can achieve an accurate output. And also when it comes to the open loop, I can't say that it is an accurate. It may be desired, but not accurate output you can expect in open loop control system. And the parameter variations, sensitivity, it is actually called sensitivity. How strong a closed loop control system to produce the desired and accurate output, and it is not influenced. These closed loop systems are not influenced by an external parameter variations like temperature, humidity, etc., and also internal parameter variations. So nothing should affect the output. So this controller as well as feedback must be in such a way that the accurate output is obtained irrespective of variations in the parameter. It may be internal or external. So, less sensitive. Closed loop systems are less sensitive to the variations in the parameter, and this is more sensitive. Open loop systems are more sensitive to the parameter variations and not that accurate what we get in closed loop control system. So, accuracy is a plus point, less sensitivity is a plus point of a closed loop control system. Otherwise, simple, economical, stable, more gain, etc. in open loop control system. So, that is the reason why you are able to measure the output. So, we can say that we should able to observe the output. So, observability is expected here, and controllability, that control on the output parameter is also possible in the case of closed loop control systems. So, when you would like to have controllability and observability aspect, closed loop control systems is the option. Whereas I mentioned almost all domestic appliances like iron box, washing machine, traffic signals, and microwave oven, all these come under the example of open loop control system. I was mentioning that transfer function is the mathematical model in S domain to analyze the given system. Analysis may be whether the system is stable or not, and speed of response. So, these are the two parameters that are to be seen with the help of transfer function. But transfer function has some limitations. Transfer function has got some limitations. That is, it is the ratio of Laplace transform of output to the Laplace transform of input, but initial conditions are ignored. So, no initial conditions are taken into consideration. Initial conditions, if you consider an electrical system, a capacitor may have initial voltage in it, or inductor, if you take, there may be an initial current in the inductor. So, that initial current and initial voltage across energy storage elements is not being taken into consideration. So, transfer function has got that limitations, but in a practical circuit or systems, initial conditions cannot be ignored always. So, that is one limitation of transfer function, and also it can be applied only to linear systems. But in fact, almost all practical systems are nonlinear, but this transfer function has got limitation. It can apply only to the linear system. Linear system, I mentioned, it should obey the law of superposition and homogeneity. So, it is justified like that. Any nonlinear system, even if you take some portion of the nonlinear graph, it looks almost linear. That means it is justified that transfer function is applied to the nonlinear systems, because that control of any parameter, it comes only for the portion of the nonlinear curve, so that it is justified though it is for linear system. Another important thing is, this is applied only to time invariant systems. What is meant by time invariant? I was mentioning in the previous class that if you are controlling the DC motor, there is an armature resistance. When the current flows through the armature resistance, that resistance of the armature varies because of the temperature. The resistance is not constant, but still we consider armature resistance is constant for our analysis, and that is nothing but time invariant. Though it is varying, but we consider as a time invariant system because that variation we ignore. Another limitation of transfer function is it cannot be applied to multiple input and multiple output systems. It is only for single input and single output systems. But in a practical or in a real systems, there may be multiple inputs and outputs. So, in such case, transfer function analysis cannot be applicable to those systems. All these limitations can be overcome by state variable approach that we see at the end of this particular subject. What kind of questions that arise on transfer function in any competitive exam? Transfer function may be given directly, and otherwise transfer function, the problems that appear on transfer function are finding transfer function if a system is given with electrical component. That means when electrical system is given in terms of R, L, C in some combinations, and active element may be voltage source or current source, then how to find a transfer function? Finding a transfer function. Next, when a system may be given in the form of differential equation. A system may be described in the form of differential equation, then how to find a transfer function? Then sometimes this transfer function may be excited by some signals, standard signals that are available, step, ramp, impulse and parabolic. Then you may be asked to find out some response. Transfer function for some response, for some excitation may be given. You may be asked to find out the response for some other input. So for that we must have an idea of what kind of signals that are available in control system. Then with the knowledge of those signals, if transfer function can be determined for various other signals. Next, last, that is a mechanical system may be given. A mechanical system may be given, then how to find a transfer function? What are the components of mechanical system? We need to see, like electrical system components, you are aware, passive components R, L, C, active components voltage and current sources. Like in a mechanical system, it is subdivided into translational motion system and rotational motion system. Translational motion system means a mechanical system which has a linear motion. Then it is said to be translational motion. An automobile, bus, car, bike, train comes under translational motion systems. Whereas rotational motion means a fan is an example of having fixed axis rotation. Rotational systems have fixed axis rotation, then translational systems have linear motion. So we need to see what are the various active and passive components of a mechanical system, then how to find a transfer function for that. So this is very important topic, finding a transfer function when electrical system is given, when differential equation is given, and some signals, the system is excited by some signals, then you may be asked to find out response or transfer function for some other signals, then mechanical systems at the last. So when it comes to electrical system, what are the components that appear in electrical system? As I said, it may be a voltage source, it may be a current source, function of time, then it may be a passive element R, L and C. So transfer function you need to apply Laplace transform to any system. So V of t is seen as V of s, I of t is seen as I of s by Laplace. So this is Laplace function, and R is also seen as R only, by Laplace and L is seen as Ls. An inductance units are Henrys. When it is transformed in Laplace form, it becomes Ls, it is an impedance. C is 1 by Cs. As you know, in the case of resistance, the voltage and current relation is V equal to Ri. So, I can write Laplace equation as V of s is equal to R into I of s. In the case of inductor, voltage across an inductor is L di by dt, ignoring initial current in the inductor. This L di by dt is written as Ls into I of s. So, you will find an additionally s term in the function. So, L is inductance, but Ls is impedance seen by Laplace. Similarly, for the capacitor, V is equal to 1 by C integral I dt. So, this is V of s is equal to 1 by Cs into I of s. When integration is there, then you have 1 by s. So, 1 by C or C is a capacitance in farads, but 1 by Cs is the impedance seen by the Laplace for capacitor. So, that is the advantage of an electrical system. When you transform given circuit into Laplace, all these three elements will become impedances. R, Ls and 1 by Cs will become an impedances. That is a great advantage when you are finding transfer function to the electrical system. So, let us see what is that advantage we have when you convert R, L, C into Laplace impedances to find out the transfer function of an electrical system. Let us consider an example, a simple example which was given even in the earlier class. This is a simple circuit given in the previous class also to find out the transfer function. Suppose you are asked to find out V0 of s by Vi of s. So, how do we start? Of course, it is simple. So, let us consider the current is I. You need to apply the basic laws like KVL and KCL. Then you develop the equations, then apply Laplace transform. So, when you see this first equation for this particular loop, you get Ri plus 1 by C integral I dt. This is equal to Vi for this polarity. First equation, this is using KVL, Kirchhoff's voltage law. Now, what is the output equation? V naught is the voltage applied across the capacitor. So, V naught is equal to 1 by C integral I dt. If you are able to write these two equations, finding a transfer function is not at all difficult, because you need to apply Laplace transform to these two equations. As I said, Vi is written as Vi of s, R is Laplace R only, but I as I of s, function of s now, plus there is an integration involved in the capacitor given by 1 by Cs and I of s. You can see now this can be written as I of s common R plus 1 by Cs. One equation you got Vi of s, then how to get V0 of s? You have already got the equation, and V0 of s is when you apply Laplace transform to this 1 by Cs into I of s. So, in both the equations you have I of s and I of s. Call this as 1 and this is 2. Now, 2 by 1. 2 by 1 is your transfer function. So, if you know this, writing equations using basic laws, maybe KVL or KCL, and then getting this transfer function is not at all difficult, because only difficulty you have when you have an integration term it is 1 by Cs. So now you get V0 of S by Vi of S, this divided by this. So you can get now 1 by Cs by this R plus 1 by Cs. You can simplify that. So simplification, anyway, it gives as 1 by RCS plus 1. This is the transfer function. Now let us change this R and C their places, swap them. In place of R you have a capacitor, and in place of resistance you have a capacitor you have a resistance. So their places are interchanged, and same is the question that find out a transfer function. So first equation is valid even here also, because this is R, this is C, and there is a current I. So equation of 1 is similar. Now there is a change in the second equation. This V0 is not now voltage across the capacitor, because now it is a resistor. So what is the output voltage now? Simply R into I, that is the current flowing. Now first equation no change when you apply Laplace transform. Now the second equation V0 of S will become now R into I of S. That is the only change when you have a swapping. Now again V0 by Vi of S, it will not be 1 by Cs, it is only R in the numerator. That is the reason why I say this is important to find out the transfer function. So you can get now this is R by RCS plus 1, and Cs also comes in the numerator. So there is a change in the transfer function when you swap these values. But what important thing is, you must know writing these two equations. So the question may come with some values. You may give capacitance in microfarads or in mega ohms or ohms. Simply you can substitute. So this is the way you need to find the transfer function. The most further, if you go to the toughest or a tough problem, like there may be a resistance and a capacitor here, and there is a capacitor even here. See that now complexity is little bit increased. You have an addition of a capacitor here. Again the question is same, find out the transfer function V0 of S by Vi of S. No change in the first equation. Of course you can write now 1 by C integral I dt, voltage across this capacitor, and plus R into I plus 1 by C integral I dt, voltage across this is equal to Vi. Now V naught is R I plus 1 by C integral I dt. Earlier problem there was only single element. Now there are two elements R and C. So writing these two equations, as I said, very important. Applying Laplace transform is not at all a problem, and then simplify it to get the overall transfer function V0 of S by Vi of S. So change is this way, you can observe. Now you can apply Laplace transform when integration is there, 1 by S and so on. If you just see another problem, that resistance and there is an inductor. No capacitor here, but there is an inductor. Say this is R, this is also R, this is L and Vi and V naught. What will you do here? I will not apply Kirchhoff's voltage law here, but I try to use Kirchhoff's current law. Let us see that the potential here, you know that it is a common node or point So the potential here is same as V naught, and with respect to ground, suppose you are asked to have the question that V0 of s by Vi of s, then how do we proceed here? So I want to apply nodal analysis here. Instead of writing a mesh equation in the previous problem using KVL, I use nodal analysis and I apply KCL. So what is Kirchhoff's current law? Assume that there is only this node. Now how to write node equation using KCL? So V0 minus Vi with this polarity by R, then this is the current in this branch, and what is the current in this branch? Plus V0 by R, and what is the current in this branch? Plus V0 by L, 1 by L integral V dt or V0 dt. So the assumption here to write or develop this equation is all the currents are leaving away from the node. With that assumption, I apply KCL. All the currents are leaving away from the node, assuming that V naught is at higher potential. So V0 minus Vi by R is the current in this branch, and V0 by R is the current in this branch. 1 by L integral V dt is the current in inductor. So a single equation you have got, this is equal to 0. Now you need to apply Laplace transform. So Laplace transform, as I mentioned, it is V0 of s minus Vi of s by R, no change for the Laplace, plus V0 of s by R, plus this is an integration here you have. So 1 by Ls V0 of s equal to 0. So you can see now there are two variables here, V0 of s and Vi of s. So you can rearrange the terms, V0 of s at one side, Vi of s at another side, and get V0 of s by Vi of s. So applying Laplace transform and simplifying is not a difficult task. What is difficult or you need to be careful is writing the nodal equation or mesh equation depending on the circuit that is given. Let us move to the little complex electrical system where you have R and L and R and C are in parallel, and R and C in this way. You can see more number of components now compared to the previous problem, that say this is R, L, R, C and R and C. Similar values are, I considered same R for all resistors and C same capacitors and so on. Now if you are asked to find out the transfer function of this V0 of s by Vi of s, you need to develop only two equations. Keep in mind that one is input equation and the other one is output equation. So as you know that L and C are given, very difficult to simplify that. You may have to consider I, then branch currents, and then finding adding the currents, and then it's a little complex procedure. But you have an advantage solving a complex electrical system when you apply Laplace transformation. So L for an inductor Laplace, it is Ls. Laplace, if you see with the Laplace i's, L become Ls, and this C becomes 1 by Cs. It is an impedance, and this C also has become 1 by Cs. Now this entire circuit is an impedance circuit, Laplace impedance circuit. So you have an advantage now if you consider this as an impedance of Z1, this impedance as Z2, they are in parallel, and assume that there is a current I. So how to write an input voltage equation using mesh analysis? I will simplify these two, where Z1 is given by R plus Ls and Z2 is given by R plus 1 by Cs, and consider this combination as Z3, and that Z3 is equal to R plus 1 by Cs. So now all three are impedances. So how to write an input voltage equation? Vi is, these two are in parallel, so Z1 is in parallel with Z2, that is in series with Z3, effective impedance in series with Z3, multiplied by I of s is Vi. This is the input equation, and output equation V0 or V0 of s is Z3 into I of s. So you have got two equations. These impedances are in parallel, and then Z3 is added to that, and you have got an I of s. So now you can find out V0 of s by Vi of s as this way, Z3 by this combination Z1 in parallel with Z2, and it is in series with Z3. That's all. So looking very complex circuit or an electrical system, but once you transform inductance and capacitance into Laplace impedances as Ls and 1 by Cs, it is so simple that this combination becomes 1, this one, and then Z3 is added to that. So finding the transfer function, substitute Z3, Z1 and Z2 these values, and you can get finally the transfer function. Any values given, you can just substitute in them, but what is important is writing these two equations. Now you consider this an RLC series circuit. This was given even in the previous class. V0. Now suppose you are asked to find out the transfer function V0 of s by Vi of s. We have seen that there is only one input equation, Ri plus L di by dt plus 1 by C integral I dt is equal to Vi, and 1 by C integral I dt is V0. Two equations are written, one is input equation and the other one is output equation. And now you apply Laplace transform to this, then you will get the transfer function V0 of s by Vi of s. You can eliminate I of s, and what you get here is 1 by Cs by LCS square plus RCS plus 1 by Cs. It gets cancelled, so you get 1 by LCS square plus RCS plus 1. So two energy storage components, please remember, that will become a second order system. If there is only one energy storage component, either inductor or capacitor, then it may be a first order system. So order is based on the number of energy storage components given in the system. So RL circuit or RC circuit will be the first order system, and RLC will be the second order system. So once you get a transfer function like this, this is actually called low pass filter. Low pass filter means low frequencies are allowed to the terminals here, but high frequencies are attenuated. For high frequencies, this capacitor acts as short circuit because Xc is equal to 1 by 2 pi Fc. So, for high frequencies, it this is very low. So, this capacitor acts as a short circuit. So, high frequencies are not allowed to the output. So, this is called low pass filter. So, for this circuit, if I want to have a high pass filter, instead of LPF, if I want to make a high pass filter, then what change I have to make here is this L and C I need to swap. So, put C here and L here. So, no change in the first equation. This is Ri plus L di by dt plus 1 by C integral I dt, but there is a change in the output equation because now there is an inductor here. Now, capacitor and inductor positions are swapped, then this become an high pass filter. So, input equation remains same, Ri plus 1 by C integral I dt plus L di by dt, and output equation is L di by dt. Now, when you apply Laplace transform, of course, you can get this as Ls into I of s, and you can apply Laplace transform to this to get so now you can get the transfer function V0 of s by Vi of s. So, inductor, when you place across the output, it is a high pass filter because at low frequencies, as you know that XL is equal to 2 pi FL. So, for low frequencies, this inductive reactance acts as a short circuit. So, low frequency signals are passed to the ground, only high frequency signals are being allowed. That is why this inductor across the output is a high pass filter and capacitor across the output is a low pass filter. So, that is the way, like once you know this 1 and 2 equations, you are able to write using KVL or KCL. Finding the transfer function is not a difficult one. Let us move to little further complicated problem where the given electrical system, it has an RC combination, then there may be an amplifier, whose internal resistance is infinity, but its gain is, say, suppose 2, and output of this amplifier is now connected to some CR circuit, and then output here V naught. Say this is R and C, this is some other values C and R. Just for the convenience, you consider as R1 C1, this is C2 and R2. Now, say the input voltage is Vi and output of this RC combination is V01 here, and after amplification V02 is applied to this CR combination and V0 is the output voltage. So, if the question comes like what is V0 of s by initial input of Vi of s. So, if the question is like that, V0 of s by Vi of s, how much? What you need to do here? So, as you are aware that for a simple RC circuit, it is a first order system, you can find out V01 by Vi. So, this V01 by Vi, as you know that 1 by R1 C1 S plus 1. We have seen in the previous problem that the transfer function of this RC network with this as output voltage, this as input voltage, you get this. Next, you can find out the transfer function of this CR circuit in terms of V0 by V02. So here you get as R2 C2S by R2 C2S plus 1 for that CR circuit. How do you get this? You know that you need to write this equation, then output equation, and then you can solve, you will get this transfer function. Now, if you assume that this is a amplifier with a gain of 2, I can write this part, relation between V02 and V01 is 2. It is like a amplifier ratio or transformation ratio. You can assume V02 by V01 is 2. Now, you see that if I want to get V0 by Vi of S is equal to V02 by V0 by V02 into this V02 by V01 into V01 by Vi. That means 3 ratios I have subdivided this entire lengthy circuit into 3 ratios. First, for this RC combination, find out transfer function. Next, for this combination, find out the transfer function. Then this is anyway given V02 by V01 as 2. So you can see now, to get this asked the transfer function V0 of S by Vi of S, V0 by V02 for this circuit into V02 by V01 and V01 by Vi. So finally you get this. So V02 this way you can assume that finally you can get the transfer function. So substitute V0 by V02, this one here, and substitute V02 by V01 as it is given in the problem 2, and V01 by Vi is this value. Whatever may be the values that are assigned in the problem, you can substitute here to get the transfer function. So this is the way you should always divide the problem into subsections and then find out the overall transfer function of the given system. Now, how to find a transfer function when differential equation is given? This is another way. In the previous section, we have seen when electrical system is given in the combination of RLC and how to find the transfer function. But now when differential equation is given, how to find a transfer function. Let us consider the example of dqy by dt square plus 5 d square y by dt square plus 3 dy by dt is equal to 5 dx by dt plus 3x. This is a differential equation given. So how to find a transfer function? So again you need to apply Laplace transform here. Okay. It's not a difficult one because you have a d cube. So it is apply the Laplace transform. As you know that if you have a dy by dt, please remember it is s into y of s. If you have d square y by dt square, it is s square into y of s. If it is a cube, you have a s cube. So same thing you need to apply here. So s cube y of s plus 5 s square y of s plus 3 s into y of s is equal to 5 s x of s plus 3 x of s. So, applying Laplace transform, then take y of s common here, s cube plus 5 s square plus 3 s, and here x of s is out, 5 s plus 3. So, once you get output and input terms separate, the transfer function for this particular problem is y of s by x of s, it is equal to 5 s plus 3 by s cube plus 5 s square plus 3 s. That is all. So, applying Laplace transform, separate them, output and input terms, and then get the transfer function. So, this is the way generally the differential equation, when it is given, how to obtain a transfer function. And a question may appear that you may be given transfer function, get differential equation also. So, it is just reverse process, you need to apply inverse Laplace transform to that. Sometimes in the equation after 3 dy by dt, say you have a term plus 10. Plus 10 is a constant. So, that plus 10 will appear even here also. This 10 is referred to initial condition. In the mathematical equation, if you observe a constant, that 10 is an initial condition, and as it is a transfer function, initial conditions are ignored. So, you need not consider this 10. So, that 10 can be removed, and the rest of the one is a transfer function. So, this can be rewritten as 5s plus 3 by s is out, s square plus 5s plus 3 is the final transfer function, ignoring the constant 10. So, this is another way of finding the transfer function when differential equations are given. This is the control system given in a differential equation form. You are asked to find out the response of the system as time approaches infinity. So, as usual, the first step when a differential equation is given, you need to apply Laplace transform to this. So, Laplace transform of 1 is 1 by s, and e power minus 2t is 1 by s plus 2. So, applying Laplace transform and then separate x of s square plus 6s plus 5 is equal to 12 into 1 by s minus 1 by s plus 2. Now, x of s you should get s square plus 6s plus 5 is taken to the right hand side. So, you need to simplify this now. You need to simplify this. So, and then you get a function in both the numerator and denominator form. So, once you get x of s, how to get a steady state value of the output, because here it is x of s. So, when you simplify this equation, x of s is given by 24 by s into s plus 2, s plus 1 and s plus 5 you get. Now, the question here is, what is the response as time tending to infinity. So, limit x of t tending to infinity is equal to limit s tending to 0 s into x of s. So, you take this x of s here and then substitute s equal to 0, you will get the response as time approaches infinity. So, you will get the answer as 2.4 finally. So, please remember, when differential equation is given and you are asked to find out the response as time approaches infinity, so you can use this final value theorem, limit t tending to infinity x of t, limit s tending to 0 s into x of s, substitute x of s here and then get the value. So, this 2.4 is the response as time approaches infinity, means steady state value. Steady state value of this particular response is 2.4. Actual inputs to the control system are sudden shock, sudden change, constant velocity, and constant acceleration. These are the actual inputs to the control system. When you take the example of sudden shock is like it exists in electrical system as well as mechanical system. If the vehicle is moving very fast, suddenly you have noticed a dig or a speed breaker, but driver has not noticed and he was going with a very high speed, then vehicle may come across sudden shock. And if you take an electrical system, there may be a short circuit or there may be some problem internally, and that may cause sudden shock even for an electrical system. Sudden change, this happens in every control system. In a temperature control system, when you wish to change the temperature from one value to another value, 40 degrees to 50 degrees, then that is a change, sudden change, and that will be the input. In a pressure control system, change of pressure from one value to another value, that may happen in any control system as a matter of fact. Similarly, constant velocity and constant acceleration are the nature of inputs to the control system. But these inputs are not available in the laboratory. So, for an engineer to analyze any system, for the inputs like sudden shock, sudden change, he needs to have a signal that is available to test the control system. So, sudden shock is nothing but there is a signal available in the lab as an impulse signal. Impulse signal is of very high magnitude for very short duration. As I said, impulse is an undesirable signal. So, this impulse signal is defined this way, that T1 time tending to 0 minus T1 to T1 delta T means the signal impulse, an ideal impulse, is represented this way with respect to time. That signal should exist only at 0 time and rest of the time signal will not appear. Impulse is that high magnitude in 0 time, but ideal impulse is difficult. So, it is always chosen that some short duration, say A, then 1 by A will be the amplitude, or if you consider this A as an amplitude, a very high magnitude, then 1 by A will be the time, so that the area of that signal is equal to 1. So, the Laplace transform of this impulse is 1. So, sudden shock is the nature of input to the control system, but I have a signal available corresponding to sudden shock to test any control system in the lab is an impulse signal. Similarly, sudden change, as I said, change in value from one value to another, then sudden change resembles in step. Step is the signal available in the lab that resembles sudden change is the actual input to the control system. Next, constant velocity, a ramp signal, and constant acceleration means it is a parabolic signal. So, these are the standard test signals that are available in the laboratory to test the nature of input for any control system are these 4. So, the impulse signal, if you add just for the convenience, all are unit impulse, unit step, unit ramp, unit parabolic, then Laplace transform of unit impulse is 1. Laplace transform of unit step is 1 by s, and Laplace transform of a ramp signal is 1 by s squared. So, a step signal, if it is a unit step, it is 1. So, Laplace transform of 1 is 1 by s, and ramp is say t, then Laplace transform of t is 1 by s square. Say a parabolic signal as t square by 2, then its Laplace transform is 1 by s cube. So, impulse, as I said, it is represented by a very high magnitude signal, and unit step is represented like this, 1 magnitude function of time, and ramp is the signal that is represented, it is a linearly varied, ramp is the signal, and parabolic is the signal function of time. This is the way it is represented. So, these are the standard test signals that are available in control system, and you should know the Laplace transform of all these signals, 1 by s, 1 by s square, 1 by s cube. Fortunately, there exists some relation between these 4 signals. So, when you start from impulse, integration of impulse is a step, and integration of a step you will get ramp signal, and integration of ramp is a parabolic signal. So, that means when you go this way, so take an unit impulse, integration of that will be the step response. Integration of step is a ramp, integration of a ramp is parabolic. In other way, if you go in this direction, then differentiation, d by dt of parabolic is ramp, and d by dt of ramp is step, and then you will get an impulse signal. So, that way, if you know the response of a system for certain input, you can find out the response of system for some other input. So, that is the good relation. You can actually remember that if you know the 4 signals, and if you know the response for a particular system, then you may be asked to find out the response for some other system, and problems will be there like this for transfer function topic. And further, you may come across some other signals other than this, is like you may have an exponential signal e power minus at. If you have this function, then Laplace transform of this is 1 by s plus a, and the response will be like this, decaying response, exponentially decay. you may find a signal as sin omega t. Laplace transform of this is omega by s square plus omega square, and it is a sine function. And you may have a cos function also. Laplace transform of that is s by s square plus omega square. So you know that sine and cos 90 degrees phase shift. You may find a signal combination of these two as e power minus at sin omega t. Then you need to combine these two functions. So it becomes omega by s plus a whole square plus omega square. What kind of response you get? You have combined exponentially decayed signal with sine signal. So you need to combine these two. So the signal will become like this. This is called damped sinusoid. Damped sinusoid because oscillations are decaying as time approaches infinity, because there is a term e power minus at involved in it. This omega is the frequency of oscillations, and this is the signal for this particular function. So you should know Laplace transform of various signals to find out transfer function or response for a particular input. Let us consider one example, that impulse response is given y of t as minus 4 e power minus t plus 6 e power minus 2t. Suppose this is the problem given impulse response of particular system. Then you are asked to find out step response. Step response. So as I indicated in the previous diagram, that if I want to get step response when impulse response is given, step response is equal to integration 0 to t impulse response. Impulse response. So if you know the impulse response, you can find out response for a step input for the same system but excited by step input, how to get the response. So 0 to t impulse response dt. So you can see that integration 0 to t minus 4 e power minus t plus 6 e power minus 2t dt. This is equal to, when you integrate this, minus 4 e power minus t by minus 1 plus 6 e power minus 2t by minus 2. So you get this 4 e power minus t minus 3 e power minus 2t. So the limits 0 to t. Now when you substitute upper limit 4 e power minus t minus 3 e power minus 2t minus the lower limit, this 0, 4 minus 3 you get. Now this will become 4 e power minus t minus 3 e power minus 2t minus 1. So this is the step response from impulse response. So when you integrate, you will get step response. Now suppose this is given step response, you may be asked to find out impulse response. Then what you have to do is to find out impulse response, try to understand that Now this is given to you as step response. You are asked to find out the impulse response. So impulse response is d by dt of step response. D by dt of step response in a reverse way. So you will get now, if you substitute this and differentiate, you will get minus 4 e power minus t plus 6 e power minus 2t. So that is the advantage of these signals. There exists a relation between all 4 standard test signals. If you know the response, you can find out the response for some other system. So this one kind of problems will appear like this. If you are asked to find out ramp response for ramp input when unit step response is given, you need to integrate that. If you want response for parabolic input, then you need to integrate the ramp response which you get after integrating this. So that is the way you should find out response for various inputs if it is given for some other input. You may have other kind of problems here, that unit step response is given. Y of t means unit step, as you know, that say R of s of unit step is 1 by s. Now you are asked to find out the transfer function. So transfer function, as you know, it is y of s by R of s. So as it is mentioned, unit step input is 1 by s. This is the response for that. This is the output y of t in time domain given. So you need to transform this into s domain by applying Laplace transform. Then you can find out the transfer function by using this ratio. So the first step, I need to get y of s here. So 5 by 2 is 5 by 2s minus 5 by 2 e power minus 2t as 1 by s plus 2 and plus Laplace transform of t is 5 by s square. So this is the first step. You need to apply Laplace transform to individual terms, and now we just simplify this. Now R of s is given as 1 by s. Now transfer function is ratio of output to the input in Laplace transform. So it is 5 by 2s minus 5 by 2 into 1 by s plus 2 plus 5 by s square divided by 1 by s. So you can simplify this as 5 by 2, s will go here, minus 5 into s by 2 into s plus 2 plus 5 by s here, because s and s square 1s will go. Now this is the transfer function you should get. Further simplification actually required, because you are ultimately to write in the numerator and denominator form. So you can take that 2s into s plus 2. So here 5 into s into s plus 2 minus this 2s plus 2. So it is 5s square plus 5 into 2 into s plus 2. Now you need to simplify this to get the transfer function. So what is that you understand from this problem? When it is written as unit step response, you should write input is unit step and the given output in time domain, transform this into Laplace domain, then transfer function is the ratio y of s by R of s, and simplify this. This is another kind of problem that will appear in transfer function problems. Now the other kind of problem that appear in transfer function is unit impulse response is given as g of t equal to e power minus t. If you remember, the transfer function can be defined in two ways. One is Laplace transform of output to the input. Otherwise, transfer function is also Laplace transform of impulse response. Because the R of S value for impulse input is 1, so transfer function is nothing but Laplace transform of impulse response. So that is given here. G of t is given as e power minus t. So if you apply Laplace transform to this G of S, it is 1 by s plus 1. 1 by s plus 1. This is nothing but C of S by R of S for impulse input. Now he is asking for unit step input. So what is R of S? R of S is 1 by S. So C of S is given by G of S into R of S. G of S is 1 by s plus 1 and R of S is 1 by s. So you are asked to find out the steady state value of the output. Means once you get the response in time domain C of t, then as time approaches infinity, what is the response? That we need to see. So here if you apply the partial fractions, this is equal to a by s plus 1 plus b by s. So you can write this as 1 is equal to a into s plus b into s plus 1. So when s is equal to 0, you get b equal to 1, and when s is equal to minus 1, you get a equal to minus 1. So you can write this function as minus 1 by s plus 1 plus 1 by s. This is C of S. Now C of t is 1 by s is 1 minus e power minus t. So the steady state response as time approaches infinity. So you need to substitute t infinity and then find out the response at steady state. So as it is asked here, steady state value of the output for unit step input, this is not the steady state value. So we should find out the steady state value as time approaches infinity. So t tending to infinity. So the steady state value is 1. So that exponential term will not be there in the steady state value of the output.